Hello and welcome back to episode 3 of Calculus 1. I am Mohammad Momenzadeh, the presenter of this lecture. So today, after all promising that we had it, we will start our discussion about the trigonometric function. So we will talk about the trigonometric function over the right triangle, and we define the trigonometric function as well over there, and later on we will talk about some identities and some calculation will be considered. So let us start our discussion by take a look at the right triangle and introducing that type of the relations. So as you can see over here in this picture, each side of a right triangle has a name, and we name the sides of the right triangle over here. The right triangle is a triangle that has one angle as a 90 degree. So if we have a perpendicular line over there, then this perpendicular line or orthogonal line with the 90 degree determine one right triangle. And if the angle of this side, this edge, is equal to theta, then we can name the sides of that triangle as follow. Adjacent is a side that is close to that angle, and the opposite is a side that is in front of the theta. And also we have hypotenuse at the biggest side of that right triangle. If we have this type of the right triangle, then we define the trigonometric value sine theta, cosine theta, and tangent theta as follows. So the sine theta is defined, as you can see, the opposite side at over the hypotenuse, and cosine theta is defined as adjacent over the hypotenuse, and the tangent theta is defined as opposite over adjacent. So with that type of definition, we have some actually identity over here. So as you can see, adjacent is always next to the angle, and opposite is the opposite the angle as well. So if we consider the theta at the other side, then the location of opposite will be changed based on that definition. So as you can see over here, we define the trigonometric function or trigonometric value based on a given right triangle. Means that if we have a right triangle over here, we have the sine theta, cosine theta, and tangent of theta. Moreover, we can define the cotangent of theta, which is denoted by COT. The cotangent of theta over here at this right triangle is defined as an inverse of that tangent. By the another word, we can define it as adjacent over there over the opposite side. Means that we have this definition for the cotangent of theta. So we have also secant of theta and cosecant of theta as well. So means that we should define also secant of theta, that we denote it by SEC, secant of theta, and also the cosecant of theta, that we write it by CSC of theta. So for the secant of theta, we have the inverse of cosine. Means that at the secant of theta, we have the following things. The hypotenuse will be calculated in a numerator of these two expressions. Means that both of them are defined as a hypotenuse over the another factor. So we have the hypotenuse, and we should divide for the secant of theta, we should divide it by the adjacent, and for the cosecant of theta, we should divide that value by the opposite. So if you just consider this type of the trigonometric values, then we have this expression. So by using this type of the definition, we have some trigonometric value. The first question that may come in your mind is about the reason that we define the sine, cosine, and this type of the thing as follow. So first of all, this type of the ratio that you can see over here are invariant. What does it mean it's invariant? It means that if I have the another right triangle with the same theta, for example, this is the another right triangle that is smaller than the previous one, but the value of theta over here is as the same as previous one, means that if the theta over here is the same, then this sine of theta is invariant. What does it mean it's invariant? It means that if this side is given, for example, by the value of A and hypotenuse by the value of C, and the other side, the adjacent of that theta, is given by B, then this ratio is as the same as a ratio that we defined it at the bigger triangle. For instance, over here, the sine of theta, based on a definition that we had, it is defined as the opposite side, which is A over hypotenuse, means that A over C, and this one is exactly as the same as the opposite at the hypotenuse of that triangle that we had. It means that it's totally equal, it's not changed, and it's happened because of the similarity of this triangle. Means that at the geometric we had some relation that guarantee that these variants are invariant. And the another reason that we define it by this method is the appearance of this expression in the geometric too much. Means that sine of theta, cosine of theta, and tangent of theta, and so on were appeared in the several topics and several theorem of the geometry, and because of that we name this type of the ratio especially as the sine of theta, cosine of theta, and so on. So you may define the different definition for them. Means that, for example, you can define one trigonometric value as a, for instance, let us give the name David of theta, for example. This David of theta could be defined as A plus B plus C, for instance, but that value should be invariant and also should be practical to appear in several theorem or several things. So by this definition that we have it over here, we have some immediate consequences, and these immediate consequences gave us some relation of this expression. For instance, let us start our discussion by the tangent of theta. So for example, if we consider the tangent of theta, which is equal to the opposite side over adjacent, then you can divide both of them, the numerator and denominator of this expression, by some value. For instance, over here, if I divide this opposite side by the hypotenuse and do the same thing for the actually denominator, then we have the following things. Means that I can divide both of them, the numerator and denominator of this fraction, by the hypotenuse of that triangle. And if I divide it over there, as you can see, we have this value. The numerator becomes a sine of theta and the denominator becomes the cosine of theta. So this is the first identity that we can evaluate it over there. Means that the tangent of theta is defined is equal to the sine of theta over cosine of theta by simply dividing the numerator and denominator by the hypotenuse of that triangle. Then we will find this relation. Let me just erase the mid part and write the identity as a consequence of this case. So the sine of theta over cosine of theta is equal to tangent of theta, and I just put all of this identity in one bracket or braces over here. Normally if you do the same thing for the cotangent of theta, means that if you have the cotangent of theta, which is equal to the adjacent over the opposite, and if you divide the numerator and denominator by the same thing, means that by hypotenuse of that right triangle, then then you will reach to the cosine of theta over sine of theta. This is the another identity that you can consider it over here. And from the first and second identity, you realize that the cotangent and cotangent are the inverse of each other. By the another word, tangent of theta is equal to 1 over cotangent, or cotangent is 1 over tangent. So this is the another identity that is an immediate consequence of our definition. Or the cotangent, as I said it, or the cotangent of theta as well is the inverse of tangent. So you can write it as 1 over tangent of theta. So moreover, we can do the same thing for the secant and cosecant. Means that if you just consider the, for example, the secant of theta, and in that definition, if you divide the numerator and denominator of this fraction by the hypotenuse of this triangle, means that if I divide it by hypotenuse, then I will reach to this relation as well. So if I just consider the hypotenuse and divide the numerator and denominator of this fraction by hypotenuse of that right triangle, then let me just extend that fraction, then you will find it as 1 over adjacent over hypotenuse, and adjacent over hypotenuse is cosine of theta. So we found this relation right now. Let me just extend the place for putting this relation as well over here. So these are our definition, and as you can see, if we just do that one, then we can have the following relations for the secant and cosecant of theta. Means that we can rewrite that one as follows: secant of theta is equal to 1 over cosine, as you can see. And in a similar way, if you do the same thing for the cosecant of theta, then you will find out that the cosecant of theta as well is equal to inverse of sine. Means that the cosecant of theta over here, let me just write it, cosecant of theta is equal to 1 over sine of theta. And the inverse is correct as well. Means that sine also can be written as inverse of cosecant, and cosine can be written as the inverse of secant of theta. So the another important identity is coming out from the Pythagorean rules. So if I name this adjacent as A, name the opposite as B, and name the hypotenuse of this right triangle as C, then based on a Pythagorean rule, you know that the C square is equal to A square plus B square. This is the relation that the Pythagorean mathematician found it in a long time ago. So by that definition, by that type of the relation, we can find one practical identity that say that the sine of theta, sine square of theta plus cosine square of theta equal to 1. So where this formula is coming from? So let us calculate the sine square plus cosine square of theta. So if you just replace that expression by the definition of sine and cosine, then you will find as the relation as follows. Let me just put the sine of theta over here, and also the cosine of theta, the definition of cosine of theta over here, and add them together. This one is square, and the second one is square as well. So let me just put the square for the denominator as well, and this one is square. Right now you can use the common divisor. The common divisor over here is hypotenuse square. So means that if I sketch one straight line clearly over here, so then we have this hypotenuse square as a numerator, as a common divisor of that one, and at the numerator of this one we have the adjacent square plus opposite square. So means that this one will be located at the numerator. So from the Pythagorean rule, we know that the numerator of this one will be equal to hypotenuse square as well, because a square plus b square is equal to c square. So we have this equation here. So we have the hypotenuse square over hypotenuse square, which is 1 over 1, because you can cancel them together. So the result is equal to 1 at the end. We have this identity right now, that the sine square plus cosine square is equal to 1. So this is the immediate consequence of Pythagorean rules. Means that by knowing that relation, you can simply realize that the sine square plus cosine square is equal to 1, and this gonna be the identity that I talk about it. So this identity, as I said, it is a consequence of the immediate consequence of Pythagorean rule. And right now, let us divide this expression by sine square and cosine square to reach to the another type of the relation. If I divide this one by cosine square of theta, then I have one relation, and if I divide this relation by the sine square of theta, then we will find the another relation as well. If I divide it by cosine square, then sine square over cosine square, based on this definition that the tangent of theta is equal to sine over cosine, can be written as a tangent square plus 1 tangent square of theta. If I divide sine by cosine and square, the total case is tangent square plus 1 is equal to 1 over cosine square, and 1 over cosine of theta is given by secant of theta. So we have secant square of theta. We reach to this expression. And moreover, you can take a root from both sides, or shift one terms to one side and write all the terms in all the expression in terms of one trigonometric values. So then you have the several identity as well. By dividing by sine square over sine square is 1. And also we have cosine square, so cosine square over sine square, based on this identity that the cotangent is cosine over sine, will be cotangent square. So we have cotangent square of theta plus 1, and on the right side we have 1 over sine square, and 1 over sine square is given by cosecant square. So we have cosecant square at the right side of this identity. So we reach to these identities based on the definition that we had it. So over here you can see these definitions. Let us put all these definitions in one example to see that how can we use them to calculate the other relation, trigonometric relation indeed. So this is a good practical question for these identities, and I encourage you to do the same thing and prepare the same table for yourself. So right now I will put one value over here and this table, and based on that value you should calculate the other related values. This is a good practicing for working with that identities. For example, I just put the secant of theta as value of 2, and based on this value I want to calculate the other relations over there. Other actually trigonometric value should be calculated. So first of all, the secant of theta is given, so the closest value to that one is a cosine of theta. You remember that the cosine of theta is the inverse of secant of theta, so I can rewrite it as 1 over secant of theta, and in this way, by substitute secant of theta by 2, then you will find out that the value of the cosine should be half. So I will put half over here. Right now I can also calculate the tangent of theta. You remember that we had this relation that 1 plus tangent square of theta was equal to secant square of theta. So based on these things you can calculate the secant of theta. So it's going to be secant square, so secant square is 1 over 4, and you can calculate the tangent of theta from that expression. So right now we have this expression. So secant square of theta means that 2 square is 4, and you can calculate it from here that the tangent of theta is equal to plus and minus. If you just rewrite the expression in terms of the remaining things, will be the square root of the secant square of theta minus 1. So by that relation we have this expression, and right now if I just put it over there, the value will be equal to plus and minus roots of 3. So you can calculate that one like this. So I will write it over here, plus and minus roots of 3. However, this plus and minus sign can be exactly evaluated in the next step, but over here up to here for practicing, it's the best things that you can do over here. Since the cosine is positive, the tangent also should be considered as a positive value, but over here we are neglecting to discuss about that sign as well. It's only needed to put it over there. So the cotangent of theta as well can be calculated easily as an inverse of tangent. Means that you can you remember that the cotangent was the inverse of tangent, so we have 1 over tangent of theta, and the result is plus and minus 1 over roots of 3. Or if I multiply that expression by roots of 3 over roots of 3, then you will find the value as follow. It's a type of the rationalization that we do it at the high school. So it's going to be plus and minus. The result will be plus and minus roots of 3 over roots of 3 times 3 will be 3 as well. So we have the answer over here as a plus and minus roots of 3 over 3. Right now you can calculate the sine of theta if you have the cosine of theta as well. If you remember that the famous relation for the sine was as follows: sine square of theta plus cosine square of theta was equal to 1. So from this expression, from this identity, you can calculate the sine of theta if you have the cosine. So from here, sine of theta can be written as a plus and minus roots of 1 minus cosine square of theta. And if you just substitute the value of cosine square, which is equal to 1 over 4, then we have plus and minus roots of 3 over 4, because 1 minus 1 over 4 will be 3 over 4. So the result is plus and minus roots of 3 over 2. So you can replace that value on a part of the blank places for the sine of theta. So I just put it over here, and at the end of the day, the cosecant of theta is an inverse of sine theta, and you can write it over here as a plus and minus 2 over roots of 3. I just emphasize about these things that if you want to get expert in that type of the relation, it's not a bad idea to do the same thing for the remaining parts. Means that one times put the value for the cosine cosecant and evaluate the remaining parts. One times put the value for a tangent and put the remaining parts, and so on. Means that just fill the blank places based on that type of the table. So in the remaining part of our discussion, we need to have these things. Indeed, we should increase our knowledge about the angle and how can we calculate it. So right now, let us consider one unit circle that is originated at the centered at the origin, and for this type of the circle that we call it the triangular circle, we just sketch the angle inside of this circle. So let us sketch one ray that is passed through the origin and determine a degree the angle over here. So we have an angle over here. Let us call this angle as an alpha. So to calculate the value of alpha in a degree, we need to have some scale. If we divide this circle to 360 part, then the sector or the splitted part of this angle determine the value of the angle. For instance, over here we have the alpha equal to 50 degree. However, if I just shift that angle to the other sides of the region that we have it over here, then the angle will be changed. For instance, over here this angle is 0, then it's going on and it's 1/4 or a quarter part of a total circle, so it's 90 degree. And if I just rotate this ray over here, then I will reach to 180, then 270, and again 360. And this anti-clockwise direction is a positive side, means that this side that we moved is a positive side, it's anti-clockwise. And if I just move on the other side, then I have a negative angle, means that if I just go forward, for example in this direction, this gonna be a negative angle, and this one is minus alpha. So we have the negative direction as a clockwise direction as well. So this determines the value of angle based on a degree. If I consider the actually length of a sector over here, means that the length of this line over here, and if I just put it in a straight line, this length of a line determine the value of angle in radian. So the area of this actually line, the length of this line from beginning up to the end, is calculated by the circumference of the circle, which is equal to 2 pi r. You remember it from the trigonometrics, classical trigonometrics, that the length of the circle is 2 pi r, and the r over here is equal to 1. We talk about the unit circle. So when r is equal to 1, means that 2 pi is the length of this circle, and as much as you selected by the angle from there, you have a radian degree as well. So it will be 0 radian, and over here that we have a quarter of a circle, it will be 2 pi over 4. So 2 pi over 4 or pi over 2. For this reason, the 90 degree is as the same as pi over 2. The 90 degree is as the same as pi over 2. And when we have 180 degree, we have pi, and at this point we have 3 pi over 2, and at the end the 0 and 2 pi are the same as well, means that 0 or 2 pi. And as much as you rotate it around this circle, you just repeat that value as well. So it's important to know how to convert the radian to the degree and vice versa. So if you just consider pi and correspond it by 180 degree, then you can calculate the corresponding values. For instance, if you have 50 degree and you want to convert this value to the radian, it only needs to use that proportion, means that 50 degree, I want to know what is the 50 degree in radian, so I will put the radian at the right side. And for 180 we have the pi radian, so I just put pi on the other side as well. Right now I can calculate the values, which is equal to 5 over 18 pi. 5 over 18 pi. In this way we can convert the degree to the radian values, and you can calculate the radian as well. This is the radian scale. So for the angle we have several scales. We can use the gradient as well, which is not used in this course, that we divide the circle to 400 instead of 360 parts, and we can calculate that one as well. But at this course we need the radian and degree, and as I said it, the pi is equivalent to have 180 degree. If you just substitute pi by 180, then you can convert the radian to the degree or vice versa. For instance, if we want to know what is 3 pi over 2 radian in degree, it only needs to substitute pi by 180, so it will be 3 times 180 over 2, and 180 over 2 is 90. 90 times 3 is gonna be 270 degrees. So this one is a converting of pi to a degree, so it will be 270 degree, which is located at that edge, means that it's over here, 3 pi over 2 or 270 degree is located at this point. So right now we realize to how can we scale the given angle. When we have an angle, then we can discuss about the trigonometric identity over there as well. So right now I have one angle, one ray that determine an angle alpha, and we have a unit circle in a round of that angle which is center at the origin. So to determine the value of the trigonometric values over here, we construct this right triangle over here to calculate that thing. So I just make this right triangle. Let us name this triangle by using the center as a value of O. The intersection of ray and circle is named by A, and this perpendicular line determine a point B over here. So right now if I want to calculate the sine of theta, then sine of theta will be equal, based on a definition, was equal to the opposite side over the hypotenuse. So hypotenuse of that one is as the same as this value, means that the opposite side of this right triangle at the triangle OAB, if you consider the triangle OAB, then the hypotenuse of that one is as the same as OA, and the OA or the hypotenuse of that right triangle is as the same as the radius of that that circle, and the radius is 1 because we had a unit circle, and moreover the opposite side of that one is equal to AB, so this AB remains over here. By the other words, the AB determine the sine of theta. So this gives us the information about the sine values. So if we consider the points over here with two coordinate, the x and y coordinate, you know that in a two-dimensional space we can have two coordinate, then the second the first exponent determine OB and the second exponent determine the AB. So this second component over here is as the same as AB. For this reason we call this axis as a sine axis. So we call this axis as a sine axis. So in this sine axis we have the value of the sine. What does it mean? For instance, if you consider one ray over here that is in 0 case, then the y value of that one, the y value of this one is equal to 0. So sine at the point 0 is 0. If you go forward and have a 90 degree, then the y value over here is equal to 1. So the sine of 90 degree is equal to 1. And if I go forward and change the ray to 180 degree, or the value of pi, then as you can see over here, the sine of theta over here, or the y value, is equal to 0. And if I just shift it to 270, means that if I just rotate it up to reaching to 270, at the 270, as you can see, the y value of this point will be the y value, or this value, is equal to -1. So the sine of 270 is equal to -1. I can gather all of these values in one table, means that in one table I can put it over here, the value of that angle and the corresponding value for the sine of theta. So we have the following things then. So you can imagine that values in your mind and calculate that corresponding trigonometric value for the given degrees. So with the similar discussion, if we want to calculate the cosine of theta, then we can see that the cosine of theta is equal to adjacent side over the hypotenuse of that right triangle. So if you just replace the value again over there, the adjacent side will be equal to OB, and the hypotenuse of that one is equal to OA or equal to 1. So because of that, the OB or this value or the x component determine the cosine of that angle. For this reason, we call to this axis as a cosine axis. Right now, the x value determine the cosine values as well. So if I have an angle again over here and I consider an angle of 0, then as you can see, the x value or this length over here is equal to 1. So cosine of 0 is equal to 1. And if I just shift that line to the 90 degree, if I just shift that ray to get the 90 degree, as you can see, the x value at the 90 degree is equal to 0. It's exactly equal to 0. And if I just go forward and try to just rotate it to 180, then as you can see over here at the 180 means that at this point the value of cosine or this length is equal to -1. So we have -1 here. And again, if I return back to a 360 or 0 degree, the value will be equal to 1 as well. So to calculate the tangent of theta and cotangent of theta, I need two more axes. Let us sketch them over here. If I continue to sketching one perpendicular line to the circle over here, let us put it over here to have one exactly perpendicular circle, perpendicular to the circle, and put the positive side over here, then I will name this axis as a tangent axis as well. So why this is the tangent axis is only need to consider one bigger triangle over here. Means that this triangle, let us call this point, the intersection of them, as a C and this point as D. Right now, if you consider the tangent of theta in a bigger triangle, not at the OAB, the tangent of theta or tangent of alpha over here is alpha. I just use theta over here. Okay, so I just follow to put the theta and change the name of this angle as a theta. So tangent of theta over here at this triangle as OCD. If I consider the triangle OCD, then at the triangle OCD, it will be the opposite side over the adjacent side. So the opposite side of that actually will be equal to CD, the segment CD, and the adjacent over here is OD, and this OD is as the same as the radius of this circle, and the radius is equal to 1. So the CD determine the value of a tangent, means that this length determine the tangent of theta. So because of that, the length of a line from the origin of this axis, which is D, determine the tangent. So at the point 0, if I have the ray over here and the angle is equal to 0, then it's cross the tangent line at the point 0, and the value of that one is increase, and so on up to the end that we have a 90 degree. And when we have a 90 degree, these two lines are parallel, and if two lines are parallel means that they never have a cross, they never meet each other. So at the point 0 the tangent is 0, but at the point 90 degree, at where we have a 90 degree, the value is undefined, because otherwise we have two parallel line. Over here we have two parallel line. And again, if I just rotate that ray to the case that we have 180 degree, the continuation of this point will cross or meet the tangent line at the point 0 at the origin. and for this reason the value over here is 0. And when we are in a 270 degree, again we have two parallel lines that we meet the points over here at actually never we will meet them, so the value over here will be undefined. So in this case you can define the actually sign of sine, cosine, tangent and cotangent in each sector, in each region. In the first region, as you can see, the cosine is positive because x is positive, sine is positive because the sine is positive, and tangent are positive. At the second region means that at this region, then the situation is changed. The cosine is negative, the tangent is negative, but the sine is positive. You can determine the sign of them in each region as well. One more line we need to determine the cotangent value as well. If I just sketch that perpendicular line to the circle at the top and put this value as a cotangent of theta, then the length that cotangent axis, then the length that we have it after meeting the ray by that line, which is happen at the same point because it's around 45 degree, the sine and tangent and cotangent are the same. So this point determine the cotangent of theta. So means that you can calculate the cotangent of theta by using this line as well. So if the angle is 0, means that we are in this location, and as you can see we have two parallel lines, so at the point 0 the cotangent is undefined, and again we have this value at here 90 degree we have 0, at 180 degree we have undefined, and at 270 again we have 0, because if you continue you will find the value as 0 over there. So over this circle you can determine as well the sign of each of these trigonometric value. For instance, at the first region all of them are positive. At the second region over here the value of cosine is negative because the x is negative, the value of sine is positive, the value of tangent, if you just consider the ray over here, as you can see the continuation of this one will meet the tangent line at negative part, means that it will be have a meet over here, and this value is negative, so the tangent is negative, and also the cotangent which determine this length also will be negative. So tangent, cotangent and cosine are negative in this region, but the sine will be positive, and so on. You can determine the sign for the remaining cases. So moreover, we should memorize the value of trigonometric function for some special angles that I just mentioned it in the next slide. So this is the value of some famous angles, and unfortunately you should memorize all of this table, and we will use it temporarily in this course. So to keep it in your mind that how can we calculate it, let us put 0, 1, 2 and 3 and 4 inside of the sine values. So after that you put that values over there, you take a root from all values. Root of 0 is 0, roots of 1 is 1, we have roots of 2, roots of 3, and roots of 4 is equal to 2. So let me just write the roots of 2. Then divide everything by 2 to just have the corresponding value. 0 over 2 is 0, then we have 1 over 2, roots of 2 over 2, roots of 3 over 2, and 2 over 2 as well, which is equal to 1. So I just emphasize about it again that to calculate the value for the sine you should put 0, 1, 2, 3, 4 and take a root from all values and then divide it by 2. Right now we have the value for the sine. Right now to calculate the cosine value, just swap the places, interchange the places, means that 1 by 0, roots of 3 by 1 over 2, and roots of 2 over 2 remains at the middle, means that you should write 1 over here, 0 at the right side, roots of 3 over 2 instead of 1 over 2 and 1 over 2 at the right side, because if the addition of them is 90 degrees, then sine and cosine are the same. So then roots of 2 over 2 in the middle. For the value of the tangent of theta, just divide sine by cosine and put it for the tangent. You remember that the sine over cosine is tangent. 0 over 1 is 0. 1 over 2 over roots of 3 over 2 will be 1 over roots of 3 or roots of 3 over 3. And roots of 2 over 2 by roots of 2 over 2 will be 1. Roots of 3 over 2 over 1 over 2 will be roots of 3. And 1 over 0 is undefined. Right now, interchange their places for the cotangent. Means that undefined replace at this part, 0 at the right side, roots of 3 over here, and roots of 3 over 3. Roots of 3 over 3 at the right side, and 1 remains in the middle. The middle will be as the same. So these are the value for the sine, cosine, tangent and cotangent. You should keep all of them in your mind. You may use some special triangle to determine the value for the sine and cosine as well. It doesn't matter. I mean, for instance, if you have one right triangle with the sides as follow, that this side is equal to 1 and the hypotenuse is equal to 2, then this determines the 30 degree. Right now you can calculate the sine and cosine and tangent and cotangent based on this value. For sure this side will be roots of 3 based on the Pythagorean rule. Right now you can calculate the sine of theta as 1 over 2. You can determine the cosine of theta at the adjacent, which is roots of 3 over 2, and so on. You can calculate it by using this special right triangle to calculate all the values as well. So there are more relation about the negative values, that all of the trigonometric function take out the negative from their values. Means that this negative comes out from the sine, comes out from a tangent. For cotangent, cosine, cosecant, secant and cotangent is as the same. The only exception is a cosine of minus theta, that the cosine of minus theta is equal to cosine of theta as well. So you should keep in your mind this type of the relations as well. So there are some more identity that you should keep it in your mind that determine the sum and difference of sine and cosine, especially for the sine and cosine. And over here, if you put A and B as the same, then you will reach to the main important relation for the sine and cosine. Let me just mention it over here, that the sine of 2A, if we just replace that A by B, then we can find that sine of 2A is equal to 2 times of sine A cosine A. Means that you can find this relation that it's equal to the 2 times sine A cosine A. We use that type of the relation severally in calculation of integral, so you should keep it in your mind, that type of the things. And also cosine of 2A is equal to cosine square minus sine square. If you just use that relation, then we have cosine square of A minus sine square of A. And if you combine the second relation with the famous relation of sine and cosine, which said that the cosine square of A plus sine square of A is equal to 1, then you will reach to some important relations as well. So you know that the sine square plus cosine square is equal to 1. If I combine these two things, then we will reach to some formula for breaking the exponent of sine and cosine. By the another word, we will find out that the cosine square of A over here, if I just add these two relations together, we will find the cosine. It will be 1 plus cosine of 2A over 2. Cosine of 2A over 2 totally over 2, and also you can find the sine square of a. The sine square of a, by subtracting these two relations, you will find the relation for sine square, which is 1 minus cosine of 2a over cosine of 2a over 2. So these two relations are important in calculation of integral of sine square and cosine square, since that in the left side of this expression we have the exponent 2, and at the right side this exponent is removed. So in a calculation of integral of cosine square and sine square, we need these two relations. So I will finish our lecture in this point, and I hope that you memorize all of these relations as well. These are too important, and we will use this type of the concept later on in a calculation of integral and some type of the calculations. So in that section that we talk about them, I just emphasize about this relation again, but it's not a bad idea to keep that type of the relation in your mind. Thank you for attending this lecture.